Okay, so I start. So we are all welcome to this lecture on Chem 101. Our topic today is chemical equilibrium. Equilibrium is something that is very, very important. It's very important in the study of physical sciences. So applying the principles of equilibrium to aqueous system, it brings us to light about the Chatelier principle, which we have seen earlier in life. And this principle is used to predict the effect of concentration, pressure, and temperature changes on equilibrium in a system of mixtures. Two Norwegian chemists, Goldberg and White, they postulated that in chemical reactions in which the forces that produce products are held in equilibrium, the forces that give us the product, and that they are in equilibrium with other forces where the reaction is not complete but partial. They formulated a law of mass action that says that each chemical taking part in a reaction had an active mass. The force they imagined to be controlling were proportional to the product of the active masses of the chemicals, either for the chemicals for the reactant or chemicals for the product. The active masses are what we call concentration. For example, in dealing with a popular chemical reaction, in which organic acid reacts with alcohol to give us ester plus water. Ester plus water is a reaction we know very well. Is a reaction that comes easily to equilibrium. That is to say that if we are talking about the force of water reaction, will be equal to a constant times alcohol times acid. That thing in bracket is what we call concentration. Is what we call concentration. For example, a simple reaction like the reaction of organic acid with alcohol to give us ester and water. The force, according to Watch and his friend, in making the alcohol and acid, they react together was proportional to the ethanol concentration and acid concentration. And then the square bracket refers to concentration, and the unit of the concentration is in mole per dm cube. Per dm cube. If we are looking at the force for the forward reaction, it will be a constant times alcohol times acid constant. Then in the same way, the force for the backward reaction will be equal to a constant times ester times times water. So at equilibrium, the idea that the two forces are balanced, so we have a constant times alcohol times acid, which will equal to a constant times ester times water. That gives us the equation we have on the board, we have on the stream, whereby a constant is equal to ester times water, referring to the product, all over a constant times alcohol times acid, referring to the reactant. Because the two constants multiply and divided by one another is also a constant, we can simplify this to give. That is Kc equals to equilibrium constant. That subscript C has been added to show that we are working with concentration. Usually it is easier to miss out the multiplication sign that is to have Kc equals to ester times water all over alcohol times acid. This expression has been verified by careful experiment. So as we found that only at equilibrium would the expression of the equilibrium constant be correct. Using gases, it is easier to measure pressure rather than concentration. That if we are using gases, we know about gases that they move at a high speed. Hence, equilibrium constant is expressed in terms of partial pressure of the gases. If we are dealing with gases, example, we have 2SO2 plus O2 to give us 2SO3. That is to say that the constant for the pressure, Kp, will be equal to P squared SO3, P squared SO3 for the product, all over P squared SO2 multiplied by PO2. Kc or Kp is used depending on whether it is easier to measure concentration or pressure. In practice, we see that solids can be ignored. Solids can be ignored because they don't create a pressure at all. And that's the equilibrium constant. Generally, the equilibrium constant of the concentration of the product divided by the reactants is used to vindicate equilibrium reaction. If you look at the reaction, we have EQ plus RR equals to SS plus CT, or we have Kp equals to PSS over PTT over PQE all over PRR. Some reactions and the equilibrium constant expression, we see that we look at the reaction, we look at the equilibrium constant. So we look at calcium triacylcarbonate 4 giving us calcium 2 oxide and carbon 4 oxide. We find that Kp is equal to PCO2. If you're wondering what's happening, then if we have H2 plus I2 to give us Hi, that's a hydrogen iodide, then we have that Kp equals to P squared Hi, P squared Hi all over PH2 all over Pi2. Then we have that H2 plus I2 equals to 2 hydrogen iodide, where we have that Kp is equals to P squared Hi over Ph squared over P H squared substring. Then we can write down the expression for the equilibrium constant for the reaction. So if we have example CO plus 2H2 to give us CH3OH, then we have now that H2 plus CO2, H2 plus CO2 equals to H2O plus CO. Then we look at units of equilibrium constant. We say that AgCl to give us Ag ion plus Ca ion, where Kc is equal to Ag ion, that is aqueous, plus Cl minus aqueous. Your answer for the value of Kc will have the unit, they will have the unit of concentration squared on mole squared Dm minus 6. Similarly, for the reaction 2SO2 plus A2 to give us 2SO3, we find that Kp is equal to P squared SO3 plus P squared SO2 PO2. The units of Kp are those of pressure squared. The units of Kp are those of pressure squared. Pressure squared times pressure, that is pressure squared times pressure, we see that we end up as pressure atmosphere minus 1. Pressure atmosphere minus 1. The units of equilibrium constant change depending on the reaction involved. Influence, if we look at the influences of chemical reaction, there is need to think about changes in 4 factors that are often used to bring about chemical changes. What are those 4 factors? We know temperature, concentration, pressure, catalyst. We say that if we're talking about temperature, or the plate of equilibrium constant it changes. Concentration, there's no change. Pressure, there's no change. Catalyst, there's no change. But equilibrium is reached faster. Equilibrium is reached faster. So temperature, equilibrium constant changes when temperature changes. It changes with temperature, but provided the temperature does not change, and the equilibrium constant is rarely a constant. Example, we look at 2SO2 plus O2 to give us 2SO3. Then we find that at this temperature, which is 298 Kelvin, the equilibrium constant is always have the value of Kp 4 times 10^24 atmosphere for that reaction. It doesn't matter the quantity of gases used, provided we are saying that the temperature is the same, doesn't matter the changes in the value of the partial pressure. Then we'll go over to concentration. We find that change of concentration of reaction of products in the reaction at equilibrium. The proportion of the reactants and products adjust themselves in such a way that Kc does not change. Once provided that the temperature does not change, look at our reaction acid alcohol plus added to give us ester plus water. We see that Kc will be equal to ester times water divided by alcohol concentration times acid. Then some of the extra alcohol reacts to make ester and water. As a result, the increase in alcohol is just balanced by the increase in ester and water. Then we go over to pressure. Equilibrium constant do not change with pressure. Equilibrium constant does not change with pressure. Example, if the sulfur dioxide reacts at 1 atmosphere or reacts at 10 atmosphere, then Kp keeps the same value. Kp keeps the same value provided the temperature is 298 Kelvin. However, the proportion of reactants and products can change just as they do when concentrations are changed. Catalyst. At equilibrium, there is no overall change in the proportion of the reactants and products, but the reaction between chemicals is because you know that the reaction between chemicals are still taking place, they are still going on. However, dynamic equilibrium is reached in the reaction of the reactants and products. This implies that at equilibrium, reactants are changing to products, and so at some rate as products are changing to reactants. So we look at the forward reaction, we look at the backward reaction. At equilibrium, rate of forward reaction is equal to rate of backward reaction. How does temperature affect the equilibrium reaction? This can be obtained from experiments that we have here. 2NO2 plus they give us N2O4, and this is an endothermic reaction. Endothermic, and when N2 plus 3H2 to give us 2 molecules of ammonia. This is an exothermic reaction. So in this case, the gases are allowed to come to equilibrium at a given temperature. This is followed by analysis of mixtures. At equilibrium, we analyze the mixtures and see what they contain to obtain their proportion. We see that from the concentration or pressure of the gas, the equilibrium constant can be evaluated. The equilibrium constant can be evaluated. The first reaction, as I said before, is an endothermic reaction for various temperatures, and the second reaction is a Haber process we are used to, and it's an exothermic reaction. Then for the endothermic reaction, the reaction that is endothermic, that is endothermic, the equilibrium is constant, and is known by so as temperature is increasing. This means that temperature rises, there is proportional more than nitrogen oxide. As temperature is increased, you have more N2O4 in equilibrium equilibrium in the mixture. On the other hand, in the Haber process, we have seen we see that it is what an endothermic reaction. It is an endothermic reaction. So we see that under that situation, we see the Haber process, as the temperature increases, the equilibrium constant becomes smaller and smaller and smaller, and the proportion of ammonia decreases as the temperature rises. That is for the exothermic reaction. For the exothermic reaction, temperature is increasing. It favors the product. More products are formed. So what products are formed? So the effect of temperature in an equilibrium is summarized by a famous principle by the French chemist Henry the Chatelier in 1888. The principle says that the, the principle says that is that am I cut off? Okay, so that that's where we are. So we see that for the reactants are favored at high temperatures. So for thermic reaction, we see that reactants are favored at high temperature, and then heat is given out, and at that high temperature, products are favored. Products are favored, and then we see that when heat is absorbed, when heat is absorbed, we are back to the reactants. We are back to the reactants. Therefore, at high temperature, the reaction will shift to the left as the proportion of the reactants increases. As increases, we see that as increases, the reaction increases, so as reaction increase, as reaction increases, more heat is required, more heat is absorbed, which leads to temperature reduction. So we see that for an endothermic reaction, this is quite different, because when endothermic reaction, for the forward product, as heat is released, then products are formed, and then at high temperature, and then at low temperatures, you have more of the reactants. Then we look at the question. Calculate the standard enthalpy changes at 298 for the reaction CO plus 2H2 to give us CH is CH3OH, not CH3H, and then CH2 C2H4 plus H2O will give us what? C2H5OH. So we should note the what is required here. Then we see that then predict what will happen if the temperature of each equilibrium mixture will increase. You look at what will happen. So we see that when we have CH3OH, we see that when we have CH3OH, that is the first one, and then the reaction is in kilojoule per mole. Then we see what happens in 2H5OH. Then we see in terms of the number of moles of gases, 2 moles plus 2 moles against 1 mole. So 2 moles plus 2 moles against 1 mole. We see that it's quite different from when we have 1 mole plus 1 mole plus one, let's say 1 mole. So that let's say in the first one, we see that there are more gases are involved in the reactant than in the product. Then we can look at the following. In CH3OH, we see what happens there in those reactions. It gives you an idea of what's happening. So we look at the assignment that we are supposed to look at. The assignment number one, N2 plus 3H2 to give us 2 ammonia, and CS, which is a solid, plus 2H to give us CH4 gas. So these are what we shall look at. Let's say this is what we shall look at in our assignment. Mm. So see, so you have CH4 gas there. So we see that here we have four giving us four molecules in the reactant, and then two molecules of gas, and then for other one is two molecules against one molecule. So let us look at the implication showing that we don't regard solid if solids are reacting, they don't exert adequate pressure at all. They don't so that we have CH3OH, and then PCO2P and P square H square. So we see what is happening there. So we are not supposed to look at the assignment which I expect each and every one of us to be familiar with, to look at the assignment, to look at the assignment, and then be sure that we understand what is happening. So at assignment, so see what is happening with the. So let's say how do I advance? Hmm? Okay, next page now. Is that so about there? Okay, that's the end. Is that the end? Okay. I thought it, I thought it's more than that. Huh? Okay, so that's what we're here. So we are looking at we have seen the forward reaction and the backward reaction, and see what happens at equilibrium. So we are seeing the forward reaction and backward there's a reaction, and then we have seen the case of two NO2 gas giving us N2O4 plus. Then that's what Brother Herbert. In this case, we look at if we're looking at this, if we're, in this case, the gases are allowed to come in contact and then reach equilibrium at a given temperature. This is followed by analysis of the mixtures of the reactants and product to know their proportion. On the concentration or pressure of the gases, the equilibrium constant can be calculated or can be evaluated. So we see that in the first of all, the first reaction, which is endothermic reaction for various temperatures, and the second reaction, which is the other process we are used to, is our friend, is an endothermic reaction. So for the endothermic reaction, the equilibrium constant increases with temperature. This means that the temperature rises. There is proportional more dinitrogen How do I take with the class response?
Just have a class response for now.
Mm,
Just
okay.
they are online.
Okay, so that's what we're seeing about endothermic and the exothermic reaction. That's what we're seeing about endothermic and the exothermic reaction. In line with what we are told by Chatelier, there's a principle. We see that for exothermic reaction, that at high temperatures, the reaction will shift to the left. Therefore, at high temperature, the reaction will shift to the left as the proportion of the reactants will increase more than will increase. We say that more heat is absorbed, which more heat is absorbed. Since more heat is absorbed, which leads to temperature reduction. For the endothermic reaction, we see that it's quite different. We see that the reactants are favored. Reactants are favored more than the endothermic reaction is quite different. We see that heat is given out. Then for the forward reaction where heat is applied and applied, what happens here? Product is favored. It's against in the case of endothermic reaction. So that for endothermic reaction, products are favored. Then for the backward reaction, we see that heat is absorbed. In this case, the temperature is increased, then the equilibrium, because temperature is increased, the temperature will shift. Where will it shift to? It will shift to the right to favor the product. This is the direction of the change that will reduce the temperature. So look at the questions we have now. When we have CO gas plus 2H2 to give us CH3OH, that H, there should be OH here, showing us is methanol, and then C2H4 gas plus H2O gas to give us C2H5OH, and they're all gaseous. Then we're asked to predict what will happen if the temperature of which equilibrium mixture will increase. Then predict what will happen if the temperature of which equilibrium system were increased. You can look at it clearly. For the first one, we say that is one mole of the CO plus 2 moles of the of 2H2 give us 1 mole of CH3OH, and then 1 mole of C2H4 plus 1 mole of H2O to give us 1 mole of C2H5OH. Then we are asked to predict what will happen, what will happen to the equilibrium mixture based on these changes, so that we can look at the following this way. We see that CH3OH, we see that CH3OH, that is formed, and then C2H5 that is formed. We look at it, let's say, clearly, and then predict what will happen. Another one is CH2O4, and then we see what will happen when we have hydrogen plus H2O gas. So we see what will happen. Kp in each one will be CH3OH, for the first one CH3OH, and then the back one will be what? The back one will be what? POCO plus P2H2, and then Kp at a constant pressure. The equilibrium constant pressure will be PH2OH over PC2H4 multiplied by PH2O. Then I try again the assignment. What will happen if an equilibrium mixture of each of the following reactions is subjected to a decrease in pressure? What will happen if there is a decrease in pressure? Look at N2 plus 3H2 gas give us ammonia 2H3, then CS plus 2H2 plus give us CH4 gas. Then look at it to make life easier for us. We see that one, they are all gaseous. And then in the second one, they are solid and gases. So we should expect the pressure to be more exact in where there are four molecules of the what of the reactant to two molecules of the product. In the second one, we have only two molecules of the reactant to give one molecule of the reactant. That's what we have under this situation. That's what we have under this situation. So that is what we shall look at critically, so as a way of trying to make life easy. So we see that we see that what happens here is that we see that that what happens is that we see which one is favored. For the systemic reaction, product is favored. For the endothermic reaction, what is happening? For the endothermic reaction, we see that what is happening, products are favored. So that two, you can see they are exact opposite of each other. So we're asked to look at so we can look at looking also at the standard enthalpy changes at that particular temperature, showing that temperature does not change for now. For the reaction to give us CH3OH and for the reaction to give us C2H5OH. So that's what we have here. So that's where we're going at chemical equilibrium. So that in the next class we shall attempt at some problems. We shall solve some problems on chemical equilibrium, looking at relating it to the enthalpy changes, relating it to entropy changes, and also relating it to what we shall look at it at all the thermodynamic terms. We know the thermodynamic terms, we know the entropy, we know the enthalpy, and then enthalpy, entropy, all of them will be examined to see how they can be calculated. So see you in the next class. It has been a wonderful day. Okay.